Hello students, in this video we'll see an example of applying the Poisson summation formula. So let's recall previously we've proven the Poisson summation formula states the following. It states that the sum over n and z of f of x plus n is equal to the sum over n and z of f hat of n e to the 2 pi I n x, right? The Fourier representation of these things. These are both periodic versions of the same function, right? And so that's Poisson summation. So what I'm going to do now is I'm going to use a particular example we've seen in the past, right? So let's consider this function. Consider f of x is our 10th function, 1 minus absolute value of x for x between -1 and 1, and 0 otherwise. So this function clearly decays rapidly at infinity, so I can apply Poisson summation to this. But recall that we proved that this relates to the Fejer kernel, of course. So f hat of xc is the sine of pi xc squared over pi squared xc squared. Okay, that's the Fourier transform. And so now here's the one cool thing we can do with Poisson summation. I can use the fact that the Fourier transform is idempotent in the sense that if I do the Fourier transform twice, it's the same as modulating the real number, the argument by negative sign, right? So in other words, what do I mean by that? I mean that if we do the Fourier transform twice, f of x, what this becomes f of negative x. I'm going to use this relationship over here, right? And in particular for this function, this is always true, that has this relationship. And so in particular, if I plug it into an even function, the Fourier transform squared for an even function is going to be just the function itself, right? So now I'm going to apply this result, this Poisson summation, to the Fourier transform itself, right? So let's do so. So in particular, what this gives me is as a consequence of this, I can say that the sum over n and z of f hat of x plus n is the sum over n in z of f hat of n. So that's f hat of negative n. So that's going to be f hat of negative of n, which is going to be the same as f. This is just going to be f of negative n. And in our case, our function's even, right? This is an even function. So this for even functions, this boils down to the sum over n and z. So in general, it's f hat of negative n, but for even functions, this is going to become f of n e to the 2 pi I n x. Okay, great. Excellent. Now what I want to do over here is I want to let alpha, now here's our application, so we'll let alpha be in R, but not in z. I don't want it to be an integer. I don't want to plug in something 0 to this. Then what we have over here is we have the sum n and z of f hat of alpha plus n is going to be what? It's going to be the sum over n and z of what? Of f of n e to the 2 pi I n x. But remember what this function looks like. Our function over here is a tent, right? Here's the x-axis, here's the f of x-axis. Our function starts over here at 1 and goes down to 0, right? Like so. There's -1 and there's 1. So at every integer, aside from 0 itself, f of any integer is going to be 0. So this sum is just going to reduce to what? F of 0. So the only term that pops up here is when n's equal to 0. So when n's equal to 0, I have f of 0, then e to the 2 pi I 0 times x, which is just equal to 1. So this whole expression is equal to 1. So what's our conclusion from this? Our conclusion from this is that the sum, n and z, of what? Of the sine squared of pi alpha plus n over pi squared alpha plus n squared is equal to 1. Okay? Now, of course, when I have sine of pi n by the product formula, what's going to happen over here? This is just going to turn into a, let's recall what that's going to give us over here. So now we have the sine of pi times alpha plus n is going to be the sine of pi alpha, the cosine of pi n, and then plus the cosine of pi alpha, the sine of pi n. The sine of pi n is going to be 0. The cosine of pi alpha is either plus or minus 1. But when I square it, nothing happens. So the whole numerator just simplifies to the sine squared of pi alpha, right? So this is going to tell us, so this whole thing is just going to simplify to the sine squared of pi alpha. And therefore, what can I say? I can write this, therefore, in the following way. I can write this as the sum over n and z of 1 over n plus alpha quantity squared is equal to what? Is equal to pi squared, by multiplying both sides by pi squared, over sine squared of pi alpha, okay? And then the cool thing from this is that I can actually do what? I can actually integrate this equation over here for alpha, for reasonable values of alpha. If I'm to formally integrate this, what we conclude? Formally, we can conclude the following from this. So hence, by integrating this inequality, we'll yield the following. We'll yield the sum over n in z of 1 over n plus alpha, for alpha not an integer, of course, is equal to what? Is equal to pi over the tangent, just the tangent of pi alpha. And this representation formula is very, very useful in a lot of number theoretic contexts. So Poisson summation is a very, very powerful tool in terms of deriving infinite expansions that relate two number theoretic quantities to each other. Thank you very much.